Hello everybody, today I'm going to explain the solution to the third problem from the 2025 US Open Contest in the Bronze Division. The problem is Mooin time 3. In this problem, which is a continuation of the first two problems, it's Mooin time. We have the same theme around the strings forming a moo, but this time around the problem asks us to find something different, which is for a series of queries to find the maximum value among triplets I, J, K, such that we have a moo string and the value of this formula is as high as possible. And basically, we have a string which consists of lowercase letters, and basically, we want to see exactly what would be the maximum value of a certain substring. So now the way you want to think of this problem is that we want to start with a slow solution. So a slow solution would be for each query to have three nested for loops which iterate over the let's say the substring, and for each of these triples check if they form a moo, and if so, to compute the value of the triplet and to see whether that gives you the actual answer and to print the maximum answer. An improvement from this idea is maybe to find for each character the rightmost position of that character in, let's say, a substring in the query. And basically, whenever we fix a character, we would reduce the amount of for loops to just two nested for loops, and that would be still too slow, but it would be a slight improvement. Now, because n and q are up to 50, then basically we want to see anything which looks decent will pass, or even the three nested for loops. And for the second subtask, the queries from 4 to 6, because we have a singular query, we have to check over the entire string. And an idea which can be valuable for, let's say, this sort of query is if we fix the middle position, then if we fix the position of the J, for example, we would want to find the rightmost letter which is equal to the letter in the middle, as well as the leftmost letter which is different from the letter we chose. And this can actually be done in a lot of ways, but with some precomputations it can actually be done in O of n. And I think it's worth explaining a bit how. So let's say that we have a string, and let's say that we fix this letter to be the middle one. Let's say that it's a P. And we can keep track using an array of where the rightmost, let's say, P is. So let's say that it's here. So we have a P and we know that it's the rightmost P. So obviously this would be the position J and this would be the position K. Now, in order to find the leftmost letter, we can also have another precomputation which tells us for every letter where is the leftmost such position. And let's say that we make a moo with a letter M. And we know where the leftmost M is, and this would be the position I. Obviously, I must be smaller than J and must be smaller than K, because otherwise the formula would make no sense. But the main gist of this idea is that if you can do some sort of precomputation, some two traversals, left to right and right to left, for each of these traversals you can find the leftmost letter equal to a certain position and the rightmost letter equal to a certain position across the entire array. Now, this will help you pass the second subtask, but still adapting it to every query would require you O of n time for every query, and the complexity would be O of n times q, which still is good, but obviously nowhere near being fast enough. So we want now to figure out a solution which works in a fast enough complexity and helps us with solving the problem. And now, some ways to think about this would be to have maybe, uh, let's say, some other precomputation, maybe a way to store where each character shows up at, because this is also important. And now, a way to think about this for every query is, we know already the structure of the string. So let's say that we have a Moo-like structure. So I will note it as a Moo-like structure. And we know that the last two letters must be equal. And also the first one must be different from the second and third one. So let's imagine that we iterate over all of the ways to choose the last two letters. So we would have a candidate, and this candidate can go from A to Z. So basically this candidate is from A to Z. And now for a given candidate, we know for sure that we want to have the rightmost letter present in that given substring, because if we go with a letter that is more to the right, then we would actually reduce our chances of having a higher potential in a way. So basically, it's always better to just go for a letter which is as much as possible to the right, because if not, then we know that the distances would still be the same in a way. And because we chose this letter to be the rightmost possible within the substring, uh, in a similar fashion, we want the letter which is different to be the leftmost one possible in the substring which is not equal to O. And here we have two cases. It's either we chose the letter which is the one we started the substring with, and in that case we can just have maybe a binary search or some other algorithm to figure out for us where the letter is. And if not, then we will have, let's say, simply the first letter chosen. So for the uh, leftmost letter, for the letter which is not, let's say, the right one, we can just go with the beginning. And now if we fix two letters, the letter on position I and the letter on position K, the most optimal choice for the letter on position J is to choose something as close as possible to the middle. Obviously, because I and K are here, the ideal position would be somewhere here. But in reality, we won't exactly get something which is exactly in the middle, so we might have some sort of a distance from the middle. But still, if it's close enough to the middle, the product will still be relatively high, because if you think of the product, so if we have something like k minus j times j minus I, because we already know what k minus I is, then basically I'm not sure if it's a theorem or anything, but if you plot what x times n minus x is, assuming assuming n is greater than x and they are both positive, then the product goes down and then goes up and then goes down. So basically, the optimum is to have both of these terms equal. And this is something I used extensively during this solution, as I basically just had a way to choose the rightmost candidate for a given position, because we can't go wrong with a rightmost candidate since the potential of that product is maximum. And the same goes for the leftmost candidate. Choosing something as much to the left as possible gives us the highest amount of candidates. And basically, in order to conclude, we binary search in the list of the letters equal to the current candidate, the rightmost position within our query. Then we do the same for the leftmost end of the query. for the leftmost character, and then for the character in the middle, we choose some binary, we do some more binary searches. And in order to recap, in this code, I pre-computed for each letter all the positions it shows up at. So a list of lists, basically 26 lists. And for a given substring, I iterated over the candidates for the last letter, the two O's. And like I said earlier in the video, for each of them, we want to find the leftmost M and the most suitable O in the middle. Basically, this allows us to have the highest potential out there. And in this first step, we find out the leftmost letter not equal to the last one. Again, a bit of casework. In most of the cases, we can actually just choose the leftmost character in the substring. Otherwise, we binary search for the position of the leftmost letter, because it might happen that the substring starts with a few letters that are equal to the same thing. So we basically want to avoid any situation in which we run out of time. Again, very standard binary search on an array. So if you read at least once about binary search, this part shouldn't be too difficult to understand. And very similarly, we also find the rightmost letter equal to our candidate. Again, another binary search. And then the third binary search, assuming that we found two suitable candidates, we want to find the letter closest to the middle of the range. Like I said, the letter closest to the middle allows us to have the highest potential. And here I fix both of the candidates, the two candidates closest to the middle. And basically for each of them, I want to see what would the product be and whether it works out for what we want to do. And in order to recap, for this problem, we relied heavily on the observation that we want the letters to be spread out as much as possible throughout the substring. And then by fixing the candidate, we used binary searches in order to obtain the answer. If you enjoyed watching this video, please like the video, subscribe to the channel, and press the bell button in order to stay notified with everything I do on this channel, as the season came to an end and I want to make other interesting content, be it educational content, also other USACO problems, and maybe code forces stuff as well. In addition, if you or someone else you know is interested in working more closely with me, you can check out the links in the description in order to join my tutoring program, a program which helped over 20 students promote to higher division during this season. So it's a very good opportunity for you to be the next one to achieve USACO glory. Last but not least, I recommend also checking out my other videos on the channel, as well as my new project where I present solutions to USACO problems. Until the next time, good luck with your summer preparation, and I'll see you in the next video. Cheers!